Assalamualaikum warahmatullahi wabarakatuh and good morning to all of you. Right, so now we are entering the last part of chapter 2, which is part 5. Alright, so without wasting our time, let's go to the next slide. Alright, you might be wondering what is eigenvalues and what is eigenvectors, right? So eigenvalues and eigenvectors are very important, okay, especially when you deal with a system of a linear equation, alright, because it can give a simpler solution if we compare to finding the solution for the system by using the methods that we have learned before. Alright, in fact, eigenvalues and eigenvector um, can maintain the relationship between the variables. Alright. Beside that, eigenvalues and eigenvectors can be expressed in as a general solution to the system. Alright. So in matrices, eigenvalue, okay, we denote as lambda. Alright, where lambda is a constant, a scalar, alright, a special set of scalar associated with a linear system of equation. Alright, so eigenvector correspond to the values or the coefficient of our matrix. Alright, when we solve the system. Okay, so eigenvalues and eigenvectors, okay, we define it by using this equation, okay, where these two x here, these are eigenvector, okay, and we have a lambda here. This is your eigenvalue, correspond to your linear equation. Alright, okay, so x is said to be an eigenvector and it must be a non-zero solution which correspond to the eigenvalue of lambda. Why do we set x to be non-zero? Because we do not want our vector to be zero vector. Okay, so if we solve this solution, x equal to lambda x, and we take this the equation on the right side to the left side, so we get this equal to 0. So we can factor the x, okay, and we left with a minus lambda in the bracket. Okay, so when we solve this equation, okay, we set our x to be non-zero. So x here cannot be equal to 0. Okay, so a minus lambda can be 0. Okay, so before this, mathematically, this means x equal to 0, a minus lambda equal to 0. Okay, this is mathematically solved. It means that from this equation, it means that x equal to 0, a minus lambda is also equal to 0. But in the matrix, okay, eigenvalues, and to find the eigenvalues and eigenvectors so that the system has the solution, we do not want our vector here, which is our x here, to be 0 vector. Okay, we don't want x here to be 0, 0, 0. Okay, so we put a condition where this x cannot be 0. Okay, so it must be non-zero. It's okay for our a minus lambda equal to 0. Okay, because our lambda here is just a constant. Alright, so understand that? Right. Okay, so once we have set our x, which is our eigenvector, to be non-zero, mean x is non-zero. Okay, therefore we can solve for a minus lambda I. Okay, so from a minus lambda I equal to 0, okay, we can find the lambda by finding the determinant of this. Okay, so A is the matrix. Okay, your matrix A is a common way. Okay, right, from equation A, x equal to B. Okay, now the difference is our B, okay, is lambda x. Okay, because now we want to find the general solution for the our system of linear equation. Okay, so we set x to be our eigenvector and lambda is a scalar to associate with the vector. Okay, so once we set a minus lambda I equal to 0, okay, we can find the value of lambda by finding the determinant of this. Okay, a minus lambda I. So determinant of a minus lambda I equal to 0. Okay, from this equation, okay, lambda that satisfy the determinant of a minus lambda I equal to 0 is called eigenvalues. Okay, so any values of lambda, which is a scalar or a constant, okay, is called eigenvalue. One is satisfy determinant of this equal to 0. So from this equation, it does not mean that this determinant equal to 0. Okay, we set that determinant A minus lambda I equal to 0 so that we can find the value of lambda. Okay, so don't make a conclusion that this determinant is equal to 0. So if that is the meaning, so you don't need to solve for the determinant, you just conclude that it's equal to 0. Alright, so we set it to be equal to 0 so that we can find the eigenvalues from there. Alright, so let's go to the next slide to see how we find the eigenvalues. Okay, so these are the steps of the solution. Hopefully you can still remember on how to find the determinant of the matrix. Okay, so you need to find the determinant for your matrix A minus with lambda I. So A is matrix A from the linear equation. Okay, and I, as usual, is identity matrix. Okay, so for 3 by 3, if your matrix is 3 by 3, so this is your identity matrix. If your matrix is 2 by 2, so it is 1 0 0 1. Okay, and so on. Alright, and then after you find the value of your eigenvalues, you find the eigenvalues. Okay, you just you need to solve for this equation. Okay, so eigenvalues, which is lambda, can be more than one. Okay, so it depends on your system. Okay, if you have a 3 by 3 system, okay, 3 linear equation, so you can have 3 solution. Okay, so 3 eigenvalues, and eigenvalues sometimes can take same solution. Alright. Okay, we go straight to the example. Okay, let's consider matrix A as this. Alright, and for your information, commonly, okay, we solve the eigenvalues and eigenvectors by using Gaussian elimination method. So you don't need to reduce it until identity matrix. It is enough to reduce it to RUF form. Okay, by using Gaussian elimination method. Alright, so the first step is to find the eigenvalues. Alright, so to find the eigenvalues, the first step is you need to find determinant of matrix A minus with lambda I and equate to 0. Okay, so you do this first. Right, what is A? A is this matrix. Okay, 3, 6, minus 8 and so on. Okay, so 3, 6, minus 8, 0, 0, 6, 0, 0, 2. Okay, do it one by one. Minus with lambda. Okay, and what is identity matrix? The matrix for 3 by 3 matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is equal to 0. Okay, so when we multiply lambda inside here, so you will have 3, 6, minus 8, 0, 0, 6, 0, 0, 2, minus with lambda, you multiply in, you will just have lambda here, and the rest will be 0. Okay, multiply lambda to the second row, so 0, and then lambda 0. Okay, multiply lambda with the third row, you get 0, 0, lambda. And this is equal to 0 as well. Okay, so each of the element here, you minus with the corresponding element of the lambda I here. Okay, so finally, you will have 3 minus lambda. See? 3 minus lambda. Next, second element 6. 6 minus with the second element of this is 0. So 6, because 6 minus 0 is 6. So minus 8 minus 0 is minus 8. And then 0 minus 0 remains 0. 0 here minus with lambda. Okay, so 0 here minus with lambda is minus lambda. Okay, so 6 minus with 0 remains 6. Okay, so next row, 0 minus 0 remains 0. 0 minus with 0 remains 0. And last element is 2 minus with the lambda here. So 2 minus lambda. Okay, so this is straight bracket, sorry. Okay, straight bracket equal to 0. Now, okay, these two straight bracket, okay, that contain your element, your matrix, means determinant. Okay, so you have two ways in finding the determinants. Remember, by adding two additional extra columns, okay, to this matrix, or you can use the cofactor method. Okay, means you expand row or column. So you can choose these two methods to find the determinant. Okay, so the easiest way is I am comfortable and I'm used to use the expanding the row or column way. So now, okay, since I look at here, the first column contain a lot of zero here. So I choose to expand the first column. Alright, so expanding the first column. Alright, so don't forget the plus minus sign because you do all the minor and cofactor at once, right? So don't forget to, in order to find the determinant, you need to consider plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, so let's go. Right, so the determinant of that equal to the first element, there, which is 3 minus lambda. Okay, because it is positive, so I put it just for your notation. And the submatrix is minus lambda 6, 0, 2 minus lambda. Okay, so next is minus 0. You multiply with the whatever submatrix is, this will be 0. Okay, so next is plus 0. Same goes to this one. You multiply with whatever submatrix, this will be 0. Okay, so now you just need to solve for this. Alright, so let us continue in the next slide. Okay, for this slide, we pass this. Okay. Okay, so continuing from here. Alright, so we get that 3 minus lambda. Okay, this one is, okay, we go this here first. 3 minus lambda. And we solve the the submatrix by multiplying A and D minus with B and C. Right? Okay, so B and C here is 0. Okay, so the only thing that you have is minus lambda times with 2 minus lambda. See? So these are equal to that. Alright, so remember we have said that this determinant equal to 0, right? So this equal to 0. Alright, so we can solve that. Minus lambda equal to 0. This is one solution. The second solution is 3 minus lambda equal to 0. Okay, for this one. Okay, and the third solution is for this one. 2 minus lambda is equal to 0. So we have 3 lambdas here. Alright, so solve for the lambda. Lambda equal to 0. So this is, just define this as lambda 1. And this lambda is equal to 3. So just set this to be 3. And this lambda is equal to 2. So this is the third lambda. Alright, so it doesn't matter which one is lambda 1, which one is lambda 2 or lambda 3. Okay, as long as the eigenvalues here are the correct eigenvalues. Okay, so now for 3 by 3 system, you have 3 lambdas, 3 solution. Okay, and sometimes your lambda, 2 of your lambda can be this, can take the same value. Okay, it doesn't matter. All right, as long as we have 3 solution with 3 eigenvector. Okay. Right. So then, now these are our eigenvalues. Eigenvalues. Okay, are you good so far? Alright. Right, so we pass this slide as well because we have found the eigenvalues for the system. Right, so once you have found your eigenvalues, now you need to proceed to step 2, which is finding the eigenvector for all the corresponding eigenvalues that you found. Okay, so remember we have, I will rewrite, okay, we'll rewrite the equation so that you can see it clearer. Okay, so do you still remember our at the beginning we solve for a minus lambda I? You still remember this? Okay, this is the first step we do to solve for our eigenvalues. Okay, so we have matrix 3 6 minus 8 0 0 6 0 0 2. We minus with lambda 1 0 0 0 1 0 0 0 1. Okay, which resulted to this matrix. Okay, minus lambda, which is 6. This is minus 8. This is 6. This is 0. And this is 2 minus lambda. Alright. Now, this is your A minus lambda I. Okay, so this is the general A minus lambda I. Okay, now we have 3 lambda, which is lambda 1 equal to 0, lambda 2 equal to 3, lambda 3 equal to 2. Right? So you're in the second step. What you need to do, you will solve the eigenvalues one by one by substituting the first eigenvalue inside this matrix. Okay, and then you do the operation needed and find the eigenvector for this eigenvalues. Okay, and then you repeat the same process by substituting the second eigenvalues, which is 3, into this equation 2. Okay, and then proceed with the operation needed and find the eigenvector for the second eigenvalue, which is 3 here. Okay, and lastly proceed with lambda 3. Okay, the third lambda, which is equal to 2, substitute into this matrix 2. Okay, this is the general one, and then okay, the general matrix form first step. In the second step, you just specify this to be 1, and then substitute with 2, lambda 2, and then substitute with lambda 3, and so on. Okay, depending on how many lambda that you have. Okay, are you clear? Alright, so now let us first solve for lambda 1, which is equal to 0. Okay, so 0, when you substitute into this, you get 3 minus 0, so you get 3. And 6 will remain, minus 8 will remain. This remain, that one too remain. Okay, this is remain 0, that one is remain 0. Okay, all the element which does not involve with lambda will remain the same. Okay, so the one that will change is just the one that involved with lambda. So you have negative lambda here. So substitute lambda 0, this is 0. So 0. Okay, so 2 minus with 0 remain 2. Okay, so this is A minus lambda 1 I, which is A minus 0 I. So it's just basically mean matrix A. Alright? Okay. So next, to find the eigenvectors, we need to reduce this matrix, okay, by using the Gauss elimination method until we get the REF matrix. Okay. Right, so for lambda 1 equal to 0, what we have is, okay, this is what we have just now. Okay, after we solve this, when we substitute our lambda 1 equal to 0, we just basically get our A matrix A back. Okay, and our x here, okay, is x1, x2, x3. Okay, this is just a defined by you. You can use other variables as well. And then remember, this is equal to 0. So all the right hand side vectors are 0. Okay, and then to apply Gauss elimination method, you need to change this matrix form, rewrite the matrix form into the augmented matrix of A and B. Okay, A and B, where our B here, as I mentioned before, is our zero matrix, which is our zero matrix. Okay, so 0, 0, 0. Okay, so this is A, this is the zero matrix. Okay, so write in the augmented form of this. Okay, so start from here. You need to reduce your matrix A here to, sorry, excuse me, my pen is broken before. Okay, so A here reduced to REF form matrix. Okay, by using the GM. Okay, so I don't want to explain more on how to do this. Okay, it is based on your practice to master the GEM or GJE, GJM, Gauss Jordan elimination method. Alright, so we go to the next slide. Okay, so to reduce to GEM to REF, okay, apply by applying the GEM. Okay, so your aim is to reduce the diagonal here to 1, okay, and then go down, reduce these 3 elements to all 0, then make sure this is also reduced to 1. Okay, so you need to follow the ERO method. Okay, so now you reduce this to 1. Okay, so R1 divided by 3, so all row 1 here will be divided by 3, and that reduce the first element to 1. Okay, so next is reduce, when you perform that, okay, you look at this. Okay, you go down, it's already 0, and you go up here, it's already 0, you come down, it's 0, and then you can solve for this one. Okay, alright, so you reduce this to 1. To reduce this to 1, you need the help of row 2. Okay, so you can multiply row 2 with 1 over 3. Okay, so you minus. Okay, when you perform this operation, all the element in row 3 changing to all 0 elements. Okay, so now you just left with this. Okay, right, so I guess we are now in our REF matrix. Okay, because all the bottom part now are all 0. Okay, so you have the main diagonal one here, but you do not have for these two. That's fine. Okay, as long as all the 0 entries are at the bottom, 0 row at the bottom, so this is already REF form, so it satisfies all the condition for REF form. Alright, and then now what you need to do is you rewrite this equation back to linear equation. Okay, so remember this is column for x1, x2, x3. So from first row here, you have x1, okay, 1x1 plus 2x2, okay, minus with 8 over 3x, 3 equal to 0, okay, because this is 0. Right, from the second row, what you have you have 0 for x1, 0 for x2, you only have 6x3 equal to 0, and from third row everything is 0, so we're just dealing with two linear equation here. First linear equation, the second linear equation. Alright, so from the second equation here, this one, we got our x3 is equal to 0. Okay, so when x3 equal to 0, this imply that also 0. So from equation 1, what we have is x1 plus 2x2 equal to 0, where x1 is equal to minus 2x2. Okay, now to solve for this equation, we need to define one variable, okay, to replace our x2. Okay, so this is called a scalar. Okay, a scalar to your x2, to represent the x2, the general solution for x2. Alright, so now I will define x2 equal to scalar s. Okay, once I do this, what happened to this equation is it will become x1 equal to minus 2s. Okay, now you have the solution for your x1, x2 and your x3. Okay, so your x3 here equal to 0 just now. Right? So if you rewrite this in the form of the solution for your matrix, for your unknown x1, x2, x3, it is equal to, what is x1? x1 is minus 2s. What is x2? x2 is s. What is x3? x3 is 0. See? So you can factor the s out, so that you have the eigenvector minus 2s, sorry, not s, 1 and 0. So this is what we call eigenvector, the eigenvector of the, okay, what you have here is the eigenvector of eigenvalue lambda 1 equal to 0. So we solved for the first eigenvalues and we got the first eigenvector. Okay, so you need to repeat the same process for second lambda and the third lambda. Okay, so we pass this slide because I have put all the necessary steps in the first slide. Okay, so as I mentioned, we just define that our x2 is equal to s. So s will be our solution for our x2, and where our s can be any value include in the real number. Okay, so now we have the general solution for the matrix system linear equation. Okay, so we pass this. Okay, so this is also passed. Okay, we got the solution from in the first slide. Right, so lambda 1 equal to 0. This is our eigenvalues. Okay, our eigenvalue, first eigenvalue. Okay, and this is the corresponding eigenvector for the eigenvalue. Alright, okay, so S is real number. Alright, so S can be any real number. Right, so proceed to the second eigenvalue. Okay, so our second eigenvalue is equal to 3. When you substitute 3 into 3 minus lambda 0, 0, 6 and 6 minus lambda 0 minus 8, 6, 2 minus lambda. Okay, so substitute 3 into this, lambda minus 2i. Okay, so what you have is 3 minus 3, you got 0. Okay, this lower element remain, the upper element also remain, only the diagonal will change. respectively to the value of your lambda. Okay, so negative lambda is negative 3, right? And then 2 minus with 3, you get minus 1. Okay, then we write this into the augmented form. Okay, so rewrite the matrix. This is matrix A. This is your X. Sorry, this is not matrix A. This is matrix A minus lambda. Okay. This is A minus lambda I. Okay, times with matrix X. This is equal to 0. We write this into the augmented form. You have this matrix next to this matrix. Okay, like this. And then reduce this to REF form by using the ERO, Gauss elimination method. Okay, so let's see what happened to it. Okay, so as usual, our aim is to reduce this to 1, but since this is a non-zero element, it's fine. We just need to make sure that this element must equal to 1 because it must follow the REF condition. Remember, the first non-zero must be 1. So you must make sure that this is 1 later. Okay, right? Because all the bottom part here are already 0. Okay, this is this satisfied the. I'm sorry for the interruption. Excuse me. Alright, so next, okay, once you make sure that all the bottom part here zeros, okay, you go to the next element. Okay, so we must settle the first row first. Make sure this one become 1. Okay, okay, so in order to reduce this to 1, you divide this by 6 so that you get this element equal to 1, and thus therefore once you divide the whole row with 6, and the whole row we must divide by 6. Okay, right, once we're done with that, our aim is to reduce the second element here to 1, reduce this to 1. Okay, so in order to do that, we need the help from the first row. Okay, so we multiply 3 to our first row so that our 2 element, which is minus 3, okay, plus with 3 from our row 1, that should give, oh sorry, I'm sorry, because of this is 1, so the bottom, this cannot be 1. Okay, because the condition for REF, the number 1 of the next row must be on the right. Okay, on the right of the diagonal one in the previous row. So this should be 0. Okay, this should be 0. Okay, you can refer back to the condition of REF matrix. Alright, so to make sure this is 0, you need to perform this operation. Okay, once you do that, this is 0. Okay, and then next is, as usual, since these two elements are 0, you must make sure the first non-zero must be 1. So this need to be 1. In order to do that, okay, you need to multiply row 2 with half. Okay, and you reduce 2 to 1. Okay, right? So this one is negative, is easy. You just multiply with minus of R3. Okay, minus 1 times R3. This will automatically reduce to 1. Alright. Okay, so in this stage, we're still not done yet, okay, because we need to remove this, okay, reduce this to 0, okay, with the same reason, okay, to satisfy the condition for REF, okay, the next number 1, okay, must appear on the right of the previous main diagonal 1 of the previous row. So number 1 cannot be here, okay, it is wrong. If you left your answer to be this is not REF yet, okay. You need to reduce this to 0, then you're done. Okay, so reduce this to 0, R3 must minus with R2, so that all the row become 0 entries. Okay, so it is at the bottom and it satisfies the REF form. Alright, so this is REF form. Okay, then you need to rewrite these two rows to two linear equation. Okay, so the first one is, this is your x1, this is your x2, this is your x3. So you have none for x1, but you have for x2. So x2 minus with 4 over 3 x3 equal to 0. This is your first equation. And the second equation is only x3 equal to 0. So this is second equation. Now we need to form the vector, okay, eigenvector, by defining the unknown with equal to some scalar, some constant. Okay, we go to the next slide. Okay, the REF form for the lambda equal to 3 is a little bit special if you compare with the first lambda. Okay, it is different. Okay, so we hold the solution yet because I want to explain to you the formation of the matrix. All right, so the first one, when lambda equal to 0, sorry, you got 1, 2 minus 8 over 3, 0, 0, 6, 0, 0, 0, and these are all 0. Okay, so this is the REF from the first lambda 1. Okay, so if you look at here, each of these unknown x1, x2, x3, they have the coefficient to them. Okay, so here for x1, okay, it is 1x1 plus 2x2 minus 8 over 3 x3 equal to 0. And the second row is 6x3 equal to 0. Okay, look at carefully and listen carefully. Okay, so you have the coefficient for x1, which is 1. The coefficient for x2 is 0. The coefficient of x3 here is negative 8 over 3. And the coefficient of x3 here is 6. Okay, so if we solve for the second equation here, okay, it is very obvious, okay, that for our 6x3 to be equal to 0, our x3 must equal to 0. Correct? Because 6 times with 0 is equal to 0. That's why we conclude that x3 equal to 0. And we apply or we substitute this x3 into the first equation to solve for the first linear equation. Okay, understand that? Clear with that? Okay, now look at our second REF for second lambda. Okay, it is 0, 1 minus 4 over 3, 0, 0, 1, 0, 0, 0, and the rest are 0. Okay, we rewrite this. Okay, this is your x1. Remember, this is x2, this is x3. Okay, so we have 0 coefficient for our x1 plus with 1 coefficient of the x2 minus with 4 over 3, which is the coefficient for x3. This equal to 0. And from the second row, we have 1 x3 equal to 0. Okay, so we have one question, two equation, and it is obvious from equation 2 here that our x3 equal to 0 because x3 there is no other solution except 0 for x3, so that is satisfied to the right hand side to be equal to 0. Okay, so that's why we conclude that x3 equal to 0. Okay, and when we substitute this into the first linear equation, that will apply this to become 0. Okay, so this one become 0. Okay, what is the the equation that we left with, which is 0 x1 plus 1 x2 equal to 0. Okay, right? So here we have equation like this. Okay, if you look at this, x1 and x2 can be represent any scalar so that this will become a 0. Okay, so here, okay, the coefficient is 0. The coefficient of x1 is 0. That does not necessarily mean our x1 should be 0 as well to get to this solution. Do you get what I mean? Okay, since that we have the coefficient of the x1, okay, which is 0, so that does not mean our x1 equal to 0. It's not similar to this at all. This is exactly x3 must be 0. Okay, so in this case, when one of the coefficient hold 0 coefficient, okay, I mean one of the variables has 0 coefficient, okay, you cannot simply declare that variable to be 0, where in this case you cannot declare that x1 equal to 0. No, this is wrong. So what you do is you need to declare your x1 equal to some scalar such as s. Okay, if you didn't do this, okay, let's say if you declare x1 equal to 0, this will automatically make x2 or as well become 0, right? If your x1 here, you declare it to be 0, it means that x2 equal to 0. So now you have all the solution is 0, 0, 0, 0. Remember our condition at the first, before we start this, at the beginning, we have stated that x cannot be non-zero. Okay, so you must make sure that you define your x1 equal to some scalar s, where s is real number. Okay, so when you do that, we won't get 0 solution, but instead we will have x1 equal to s, x2 0, x3 0. Okay, this is solution for x1, x2, x3. Okay, so you can factorize it to be like that. Okay, and x2 will be 0. Okay, because based on this equation, when you multiply whatever the value of x1, when whatever the scalar that we define for x1, even though it is s, but we multiply it with 0, so it becomes 0 here, and then what we left for x2 is only 0. Okay, and for x1 we just define it as s, so let it be. Alright, factor it out, you get this. Okay, so make sure, okay, this situation apply. Okay, you define your x1 even though it is 0 here. Alright, just to make sure you won't get 0 solution for your x. Okay, so this is a special REF form. Okay, you have for x1, x2 the coefficient, but you have none for x1. But for this one, if you look at this REF, you have coefficient for x1, x2, x3. So complete for all three unknown, you have 3 coefficient. Alright, I hope that is clear. And lastly, we need to do for x3. Lambda 3, which is lambda equal to 2. Okay, repeat the same process, right? After you substitute lambda into equation lambda minus lambda 3i equal to 0, okay, you got this matrix, okay, matrix A minus lambda I, okay, times with your x equal to 0. Then write into the augmented matrix, okay, you reduce these to REF matrix. Okay, with just one ERO, you have reduced the matrix to REF form. Okay, so for this one, if you check, you have the coefficient for x1, you have the coefficient for x2, you have the coefficient of x3. So you can proceed as usual. You'll rewrite this equation. Okay, so the first one will be x1 plus 6x2 minus x3 equal to 0. This is your first equation. Your third equation, you have 4x2 minus with 3x3 equal to 0. This is second equation. Alright. Okay, so what you do here, you can let any of the variable unknown here, okay, variable here, to be constant as or so on. Okay, so here I will let my x3, okay, equal to s. Okay, so when I apply this to second equation, okay, I got x2 minus 3s equal to 0. Okay, which means our x2 is equal to 3s. Okay, now I have x3 equal to s, x2 equal to 3s. Substitute both into the first equation. So you will solve for x1 plus, what is our x2? 3s, so 6 times 3 is 18. Okay, 18s minus with 8 times with s, is it? Yeah, 8 times with x3, so s, so 8s equal to 0. So your x1 is equal to minus 10s. Right? And rewrite that into vector. Okay, we write into vector. You have this vector, which is the eigenvector for the third lambda. Okay, now you have completed all the eigenvalues and the eigenvectors for your system. Okay, so you're done with that. Okay, next for the second example, let us consider this matrix B. Okay, let us find the eigenvalue and the eigenvectors by using the GAR method. Okay, so we will apply the same method as we did before. First, we need to find the eigenvalues, okay, by finding the determinant for matrix B minus lambda I. Okay, so this is your matrix B just now, and this is lambda that has been multiplied to your identity matrix. Okay, so subtract B with lambda I. Okay, so this is the matrix of B minus lambda I. Okay, you need to find the determinant of this matrix, okay, by using the two methods. Okay, I do not need to explain anymore because I did in many of the previous slide before. Okay. Okay, so the step continue. Now, I find the determinant for this matrix by expanding along the first row. Okay, expanding the first row. So don't forget, because we solve the determinant at once, so we'll do the cofactor and the minor cofactor things all together with the expanding the row. Okay, so you need to consider the plus, minus, plus sign. Okay, so minus, plus, minus, plus, minus, plus. Alright, so what is the corresponding value of the first element? The first element is lambda I. Positive lambda, positive times negative lambda. Okay, positive 1 times with minus lambda is minus lambda, and the corresponding submatrix to the row is minus lambda 1 1 minus lambda. Okay, so next is negative 1. Okay, so everything here negative 1, and the corresponding submatrix is 1 1 1 minus lambda. Okay, and the third and the last one is positive 1. Okay, and the corresponding submatrix is 1 negative lambda 1 1. Alright, then you need to solve this by multiply the A with D minus with B times C. Do for all. Okay, multiply that with that minus with that. Okay, then you need to solve this equation. Okay, so you need to do whatever you need for the operation. Okay, then you get this. Okay, for this quadratic equation you need to factorize it. Okay, so that it is easy for you to solve for your lambda. Alright, so this is equal to 0. Alright, so solve, now you can solve for your lambda. When you equate your equation with 0, okay, so you will have the first one is lambda minus 1 in the bracket. This is squared equal to 0. Okay, so we squared both sides. You will have lambda minus 1 equal to 0. Okay, so you will have lambda 1 and lambda 2 equal to 0. Okay, because you have because this is a square, so you must have two factor. Okay, two root. Okay, so we define as lambda 1 and lambda 2. Sorry, this is equal to 1. Okay, so this is equal to 1. Okay, so 1, bring it to the right hand side, so we got 1. Okay, from the second equation, lambda minus 2 equal to 0, so your lambda is equal to minus 2. So define this as your lambda 3. Okay, so now you have two eigenvalues that have same values, which is 1, and you have one different eigenvalue, which is minus 2. So here you will perform 2 times of GEM to find the eigenvectors. Okay, where the eigenvectors for lambda 1 and lambda 2 are equal. Okay, next we proceed with step 2. Okay, we want to find the eigenvector for the corresponding eigenvalues. Okay, so for first we go with minus 1, which is for our lambda 1 and lambda 2. Alright, so when we substitute lambda 1 into our matrix, okay, to the diagonal part, okay, to the diagonal part of the matrix B minus lambda I, this is the matrix that you have. Alright, now you need to rewrite this to the amount by rewrite it in the augmented form, okay, to reduce it to RAF form. Okay, now this is our augmented matrix. Okay, so we need this to remain 1. Okay, this we need to reduce to 0, reduce to 0, reduce to 0. This is must be remain 1 and must remain 1, or at least become 0. Okay. Alright, when we perform GEM, okay, by using the ERO, by applying 2 steps only, we are now reducing our matrix to RAF form, where the 2 rows at the bottom are 0 entries. Okay, so from here we can come out with our equation x1 plus x2 plus x3 equal to 0. Okay, which is the only equation that we have. Right, so the solution for the eigenvalues, okay, since we just have only one solution, one equation, so if we rearrange our x1 to be a subject, right, so we have minus x2 minus x3. Alright, so here we cannot just define our let our x2 equal to s, but we also must let our x3 to the other constant, okay, other unknown or variable, so that it can x1 can be solved. Alright, so here what I do is I let x2 equal to s and x3 equal to 2, and therefore our x1 is equal to minus s minus t, and thus the corresponding eigenvectors for our x1 and our x2, which is minus 1, is equal to this. Alright, what is our x1? Our x1 is this. So minus s minus t, and we define our x2 equal to s. Okay, substitute here, and our 3 we define equal, we let it equal to t. Okay, and here we can separate this to two vector. Okay, s with s, t with t. We separate them. Okay, so we have minus s, we have s, and we have 0 here. Okay, and we plus with minus t, so at that it become minus s minus t. Okay, so s It's only S there, so no 40. And for the third one, we have T. Okay, where this is equivalent to, we factor the S out, minus 1, 1, 0, plus, we factor T out, minus 1, 0, 1. Okay, so this is the solution for x1, sorry, the eigenvector for our lambda. Okay, here both our f and our test are real number. Okay. Okay, so since we have equal value for the eigenvalues for our first and the second eigenvalues, so we're done with the first GEM, okay, to represent two eigenvalues that are equal, right? So the last one is for lambda 3 that is equal to 2, and when we substitute 2 or to our lambda 3 in the matrix, so this is the matrix that we have. Okay, now we proceed by writing the augmented form of the to solve the eigenvectors. Right, so this is the augmented matrix. As usual, proceed by using the GEM. Okay, apply the ERO, reduce this to REF form. Okay. Okay, so the process of GEM by using the ERO, we have like 1, 2, 3, 4, 5. Okay, 5 operations. Okay, 5 operation here until we reduce our matrix to REF form. Okay, so you just follow the same step as before. Okay, so our third row are all zero entries, and this is from our second row. Okay, we have x2 minus x3 equal to 0, and when we write our x2 as a subject, means that x2 equal to our x3. Okay, and this is from our first row. We have x1 minus 2x2 plus x3 equal to 0. Okay, so from between 1 and equation 2, okay, it is easier for us to start from equation 2. So we let our x3, okay, equal to s, so that our x2 is also equal to s. Okay, where our s is real number. Okay, and we substitute x3 equal to s, x2 equal to s into our first row equation, and we got our x1 equal to s. Okay, this is s, that is minus s. So we have x1 minus s equal to 0. So our x1 is also s. Okay, so when we replace all the x1, x2, x3 in the matrix form, so this is what we got. Okay, so s, s, s. When we factor s out, we have 1, 1, 1. Okay, so we're done. Alright, so that's it for eigenvalues and eigenvector. Alright, so hopefully you understand and can cope with all my explanation, but if you don't, please don't hesitate to ask. Alright, so don't forget to do the revision from the first page of the chapter 2 until the last page of chapter 2, because everything will be covered in your test 1. Okay, everything. Alright, so make sure you understand all the operation, all the methods, okay, all the properties, okay, the everything lah. Alright, so if you have any question, please ask. Alright, So thank you very much. See you again in the next lecture.